Assalamualaikum and hi to my fellow panels. My name is Arif Amis Ar-Rashid bin Musli. Under the supervision of Dr. Muhammad Ali, going to present to you my final year project presentation about heavy aerial lift drone towards full-scale autonomous flying taxi, grab car, a feasibility study. Let's start with the introduction. Over the past years, drones have been developed with better features and implemented in the nature of global business. On the figure shown is the EHang 184 that are commercially available in the market right now. EHang 184 consists of 8 propellers with the aim to cover medium to short distance communication and transport problems. In addition, this passenger drone EHang 184 is eco-friendly and is equipped with fail-safe system that can land to the nearby area if one of the components fails. Although EHang is currently available, however, it is still not ready for public use. It is currently running on flight tests. According to the article on Planet Energy in 2018, a total of 24% of CO2 emission fuel combustion came from transportation. This is where the passenger drone project will take place. Based on previous study, drones are used for parcel delivery, agriculture, surveillance device, and others. However, in order for passenger drone to transport humans, drones needs to be redesigned in such way that it can withstand an average human weight. Next, on the material of the passenger drone, we should compare the drone design with the existing weight of the passenger drone that are currently available in the market. To design a passenger drone that is light in weight, we should choose a suitable material such as aluminium alloy 6061. Proceed on the objective of this project. First, I should prepare a conceptual 3D design of the full-scale autonomous passenger drone. Next, to identify a suitable material for the passenger drone. Next, after the drone have been designed, I should make test and analysis using finite element analysis (FEA) using CAD software. This project will be focused on prepare a conceptual 3D model that are capable for at least support one passenger. On the material, the choice of material for the body frame and other part must be as light as possible so the drone can fly smoothly. On the analysis, the structure design that have been made should be run through FEA, finite element analysis, using CAD software such as SolidWorks and CATIA. Next, on the literature review, the figure shown is the passenger drone design made on CATIA V5. The rotors that are placed on the quadcopter are directly responsible for creating the required thrust and torque around the rotation core. The rotor 1, rotor 2, rotor 3, and rotor 4. Quadcopter indicates the number of rotor arms and the propeller. According to study, to create a drone, we must have at least 4 propellers. Why? Because 4 propellers is the economical way to produce a drone. Doesn't matter how many numbers of propellers that we are going to design on our drone, as long as the numbers are even numbers, because the number of propellers can determine the stability of the drone, because more propellers equals to more stable flight. You can have less than 4 propellers for your drone. However, without precisely balanced load, you will have little control to your drone. Next, we should have a 4-point to have a variable thrust so the drone can hover smoothly and stable. Next figure show the basic flight movement of a quadcopter and a working principle of a quadcopter. On the left side, you can see the bar indicate green, white and red. The red color shows the high speed movement of the motor and the green shows the low speed movement of the motor. For example, in figure E, it shows the drone in hover mode. All the rotors rotate at the same speed and at a high speed rotation. Another example is on figure B. It shows the drone is moving forward. The red colors of the rotors shows it spin at a high speed to push the drone forward. On the working principle of a quad rotor, there are 4 example: throttle control, pitch control, roll control and yaw control. Let's take example on the throttle control. The orange color indicate the rotor of the drone spin on a high speed. The blue indicates on a normal speed. For the drone to move upwards, all the 4 rotors have to spin simultaneously at a high speed. While when the drone is moving downwards, you have to spin, the rotor have to spin at a normal speed so the drone can hover downwards. Another example on the yaw control. For the drone to spin around, on the yaw control, for the drone to yaw on the left side, the drone left and side rotor should be paired together and spin on the same direction, while the rotor on up and down also should be paired together and also spin at the same direction. For a drone to give a particle power input and produce the same amount of thrust, the rotor should be made up of components with the same design specification and expected performance. The angular momentum of any of the 4 rotors produce a torque around the vehicle inertial mass center that can be effectively counterbalanced by the torque generated by the opposing rotor. On to the next part on methodology. The infographic shows the method that have been done to do the project successfully. First, on the literature search on the passenger drone design requirements, then sketch on the initial 3D concept. Once the initial 3D concept has been satisfied, we will proceed on the CAD software. The CAD software that have been used is CATIA V5. The design have been made on the CATIA V5. After the design have been satisfied, we will then I proceed to the material. I've chosen the material aluminium alloy 6061. Aluminium alloy 6061 is chosen because it is one of the lightest weight material and it is suitable for aviation use. Lastly, on the FEA, make test analysis of the design using finite element analysis. This is done to make sure the design has met the design requirement from the literature search. There are 3 analyses that have been made in this project that have been made on the drone design. First, stress analysis. Second, frequency analysis. Third, impact test. On the stress analysis is to determine the critical stress act on the mainframe. On the frequency analysis, to study the dynamic characteristic of the structure under vibration. Impact test. Impact test was made to compare the impact of dropping the passenger drone at different heights with different material. For example, in this project, I'm using aluminium alloy 6061 and steel AISI 1020. Lastly, factor of safety, FOS, to calculate the factor of safety of the structure. Okay, figure shows the final design concept of the passenger drone that I have designed on CATIA V5. There will be 3 parts on result and discussion: static analysis, frequency analysis, and impact test. On static analysis, as you can see, as figure shown, is the result from CATIA V5. The result is from the static analysis that has been done on the mainframe of the drone. On the left side, result of von Mises stress acting on the mainframe. On the left side is the translational displacement acting on the mainframe. The data have been tabulated on the table below. As you can see, the maximum von Mises stress occur on the drone using material aluminium alloy 6061. The maximum von Mises stress is 3.68 megapascal, while maximum translational displacement is 0.182 mm. Based on the maximum von Mises stress value obtained from the result, I can calculate the factor of safety of the structure. The factor of safety can be obtained from yield strength of aluminium divided by the maximum von Mises stress of the structure, where yield strength of aluminium is 5.515 divided by maximum von Mises stress, we will get 15. High value of factor of safety clarify that it is 50 times stronger than the yield strength of aluminium, thus it is safe. On the maximum von Mises stress obtained, the maximum von Mises stress obtained is 2.65 megapascal. It does not exceed the maximum yield strength of aluminium alloy 6061, that is 5.148 megapascal. This clarifies that the passenger drone mainframe would not fail when the force of 1000 Newton was applied during operation. Lastly, the maximum translation displacement is 0.182 mm, and therefore it does not have a significant impact on the mainframe. On the next part is frequency analysis. Both figure B1 and figure B2 shows the result obtained from SolidWorks. Figure B1 shows the dynamic behavior on mode 6 acting on the mainframe. As you can see, on the red color part is the maximum amplitude of vibration indicates on the structure, and the lowest one is the blue color, the minimum value. Same goes on the right figure. The red color shows the maximum value of amplitude of vibration at 0.393 mm. On mode shape 6, the result shows when the structure vibrates at 4.7762 Hz, while in mode shape 10, it shows the dynamic behavior of the structure when it vibrates at 47.765 Hz. From the figure, it shows the dynamic behavior of the mainframe as shown in figure B1, B2. It shows that the structure resonates at different value of natural frequency. Different color display of the structure resonating from low to high, low blue and high red. Figure B2 shows deformation of the body when it vibrates at 47.765 Hz. In mode shape 1, the maximum amplitude vibration is 0.135. It shows that it vibrates more in the middle of the frame, while in figure 3.4, it vibrates more at the bottom part of the structure. As you can see, from the result I observed, based on the result, I have observed, the structure start to deform is at 3.8413 Hz, mode 4. Finally is on the impact test. I have made an impact test to compare between two materials. There is aluminium alloy 6061 and steel AISI 1020. All the data that I have calculated, I have tabulated it in table C1 and table C2. This is the formula that I have used to calculate the data. First, kinetic energy, second, velocity, and lastly, to calculate the average impact force. Next, I will explain how I calculate the data. Assume that the distance traveled after impact is 1.5 meter. After that, the kinetic energy formula was used to calculate the total impact force as shown in the table C1 and C2. The result shows the total impact of the main frame from various heights. The height range from 200 to 800 meters. Of course, from both material, the highest total impact force value will be obtained at the highest point of the structure to drop. Also based on the result, as you can see, the steel AISI 1020 has higher impact force result compared to aluminium alloy 6061. This shows that the impact of heavier weight will result in a higher force of impact. Thus, that's why I have choose aluminium alloy 6061 compared to steel AISI 1020. To conclude, the design of the mainframe and the boom structure has been successfully completed. Apart from that, the simulation done using CATIA V5 produced suitable values. The maximum volume stress obtained does not exceed the maximum yield strength of aluminium alloy 6061. On the frequency analysis, without a proper damping, the structure eventually will break apart if the structure constantly vibrating at a high frequency. In addition, the computational analysis conducted effectively quantified the safety factors of the main factor. High safety factor value obtained shows that the design is safe. Based on the scope of study, material for the body frame must be chosen wisely, and must be light enough without holding too much weight so that the drone can fly smoothly. As for the recommendation, propose that the drone is to be manufactured using a material that is even stronger than aluminium alloy 6061. For future study, if all the design requirements have been satisfied, we should move on to computer fluid dynamics. Is an aerodynamic analysis that will be conducted on the frame of the drone design. And that is all for my presentation video. Thank you for your time and your attention for reviewing my presentation video. If there are any inquiries, you can contact me on my email and my phone number listed below. And that's all. Assalamualaikum. I hope you have a good day and stay safe wherever you are.